Hi. Now let's discuss more about the mode of bioinstruments and performance characteristics. So the operational modes of bioinstruments. Let's think about this measurement of bioinstruments. Usually we want to measure something related to biological system. So there are two ways of general types of measurement. One is direct measurement and the other is indirect measurement. So which one's better? So in general, let's think about the signal aspect. Let's say I want to measure the activity of a brain signal, especially the neuronal signal, neuronal electrical activity. Then there's an instrument called like EEG, electroencephalography, which measures the electrodes, electrical signal through the scalp. And then it's becoming hard because inside the neurons, inside the brain, that electrical activity has to go through the skull and the scalp, which has pretty low electrical conductivity. So in terms of signal aspects, to measure it directly, you may have to do a brain surgery, remove the scalp, remove the skull bone, and put directly these electrodes on top of your brain, and which gives a best signal, better signal. So if possible, direct measurement would be better for the signal aspects, but not necessarily for the patient. Okay, so those direct measurement of the electrode is called ECOG. So for example, microelectrode array, or we call it MEA, can be measured in direct contact. And so that means it could be invasive. So maybe it gives a better signal, but it may be invasive. Another example is a indirect measurement is functional MRI. So functional MRI is taking MRI for repetitive times while the subject is performing a task, so that we can find out how to relate the task to the specific region of the brain, which indirectly indicate the neural activity. So which is indirect, so it's not invasive, and maybe the signal itself is weak, that you need to do an extensive image processing and analysis to be able to figure out a meaningful data. Okay, so that's the difference between direct and indirect measurement. Now let's discuss about majority of the signal itself are in fact continuous data, which is by itself an analog. However, majority of our processing is in fact done by computer, which means it's digital, and we have to sample in terms of time and in terms of level of the quantity of the signal itself. So the data acquisition can be divided as sampling versus continuous, or digital or analog. So while most sensors are analog, but the signal has to be converted into digital for our processing or transmission to another form of data, which we call as ADC, or analog to digital conversion. So digital signal, there are two ways to consider this. As a first, in terms of time, it's a discrete time signaling. We call it as a sampling. So discrete time as a sample, because time is itself continuous, but for our purpose, we usually sample so that we don't measure the whole lot of data, only meaningful time interval. And at the same time, also in terms of the quantity of the signal, we use discrete level amplitude, or we call it as a quantization, because even the amplitude or the amount of signal itself is an analog quantity, but for us, when we measure and for processing for digitally, we have to quantize it. So here's an example of this. So the x-axis is time, and this purple line is, let's assume, the true analog signal. However, in terms of time, we cannot take the whole signal, so that we sample it here. You see this vertical line, it indicates the time interval, which is regular, but we are sampling the time. And during this sample, we actually get the value of this black dots as we are measuring these dots. Okay. Now, I want to describe a very famous and one of the most important in our measurement, that's called Nyquist criterion. So those who are in engineering who usually have learned about this. Those who are maybe non-engineering background may not be very familiar with this. So this is also called as Nyquist-Shannon sampling theorem. So what is sampling theory? So sampling theorem describes that, let's say the original signal has a certain frequency up to certain, which we call as a bandwidth. So those bandwidth of the original signal, if we are going to sample this at least more than twice of this original signal's frequency bandwidth, then we actually can completely recover the signal. So that's called a sampling theorem. So any continuous signal of frequency bandwidth, let's say f sub bw, that can be fully reconstructed from its discrete time samples, even if we are sampling it, but with high enough sampling rate, such as sampling rate of higher or the same as here is it twice of the bandwidth. So this is the kind of the point. Let me give you another picture over here. So what happens if we do not meet this sampling theorem or Nyquist criterion? Here's one quick example. So let's say this red curve is at the actual signal, while we are sampling only these black dots. Look at this. So we actually kind of getting these black dots, but if we are connecting these black dots as a sinusoid, we realize the shape of sinusoid is completely different from the original. So we are actually misleading the signal by our slow sampling. So how to prevent this? So to prevent this, we may need to condition the signal so that if we know our sampling frequencies like Fs, then we know that we can only reliably reconstruct half of the frequency Fs. Then higher than half of the frequency Fs, if we know that's not that important, it probably is better to condition the signal by putting a filter, low-pass filter that removes higher than half of the sampling frequency before we actually detect digital analog to digital conversion. So this is a general guideline. So by using anti-aliasing low-pass filter at a lower than bandwidth cutoff frequency prior to sampling at higher than twice of the bandwidth, which is Nyquist criterion. And we'll get back to this again later. So let's discuss the next is a real-time and delayed operation. So real-time signal processing sometimes is essential for bioinstruments that needs a feedback, real-time feedback. However, sometimes some delay can be acceptable for output of display and transmission systems, which means you can measure real time, but you may need some time to process, let's say display to the patient, like, several seconds later. If that's okay, that is fine with delayed operation. So Now let's discuss about quantization error. As we are collecting the data into digital form, we are always limited by the amount of data quantity. So even the amount of data, we're not using analog, but digitized. So we have a certain level and we have to assign it for the original analog data. So this we call as a quantization. So it inevitably involves certain amount of quantization error. So let me show you this figure. Sorry about the quality of the figure, but let me explain you. So analog to digital conversion, quantization error. So the x-axis is time. That blue curve is the actual continuous analog signal. However, let's assume that over time, we are only sampling at these discrete time. Let's say these dots and these dots. And then when you look at these black lines, so the y-axis is the signal as a voltage. You see this line is discrete digital level, which means, in fact, we can only collect the data to these points, not in between. But the actual analog level, for example, here is in between, then this will be assigned to its closest one, which is this part. So that is the reported digital level. And let's move another data point here. Now this one is closer to this digital level than this, so that it will be assigned to report as digital level. So this amount, it will be quantization error. As you can see, if it, what would be the biggest quantization error? That will be exactly half of discrete digital levels. And so in this kind of discrete digital level, we can say what is the resolution. That resolution is this each of this digital level difference. And now I want to show you one more time of the aliasing inaccuracy. So if Nyquist frequency is not exactly met, what will happen? So these, again, blue lines are true analog signal. Of course, if we are sampling it for very, very, very fast, that we capture all this figure, then that's no problem. But in practice, we are always kind of limited by the sampling frequency. However, the sampling has to be fast enough. So when the sampling is not fast enough, like this case, what will happen? Let's look at this dot, which is a sampling time. So let's say here, it hits, 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 hits. Then we only know this red point. So we will reconstruct this as a sinusoid. Then you will see this, a new curve will be formed as a reported digital level, which you can notice it's completely different from the original signal. In this case, you can see from here to here, there are like one period of this reported digital. In fact, there exists 1, 2, 3, 4 period are there, while we have only 1, 2, 3 are here. So this is completely different. And that's caused by not following fast enough sampling or not fulfilling Nyquist criteria. Let me show you one example that I took a video with my iPhone. So conceptually, here, it's easier to understand. So let's say F is the signal frequency, which is the curve, while F sub S is sampling frequency. If we have sampling, which is faster than twice of the original signal, that means we have this multiple dot points, which we will recover almost completely for the original signal. Then what happens if our sampling is exactly twice of the original frequency? Then it becomes a problematic, or it can be okay or problematic. Let's see why. So if it happens to be the phase of the sampling happens to be like this meeting a top down, top down, top down, then we can reconstruct this as a original frequency. However, if you shift this like only pi over 2 phase, then you will get this. What happens for this sampling? It'll give exactly the same value that the original signal will be interpreted as it's just constant value. So this is a problem. That's why your sampling has to be at least faster than twice of the original frequency. And what happens if your sampling is slower than this? Then you see this kind of phenomena that it will not accurately present or represent the original signal. So you are distorting the original what's happened. In fact, this happens all the time in our daily lives. And let me give you an example. So I took with my iPhone, I took a propeller airplane, and I watch with the iPhone will have a 30 frame per second, which is okay for our video, but the propeller can rotate even faster than. And so let's see what happens here. Note that this sounds a little bit strong, so let me reduce. Okay, so by default, this iPhone video is 30 frames per second. Let me start. So look at this becomes slower. In fact, the propeller is not slow, it just looks slow. And you see it rotates one way, now it rotates the other way. Look at that. The direction changes because iPhone's 30 frames per second remains, sampling is the same, but the actual signal is actually faster. So you see it changes. Let me play it one more time. So look at that, it looks very slow because now it's almost the same. So it becomes slow, and it moves, rotates one way, and you realize it moves this direction and the other direction, which is completely wrong because the propeller moves always the same direction. And that is coming from this not following Nyquist criterion. So this is we call as an aliasing. And this happens all the time. So for example, like bandwagon effect, you see the wagons of here, sometimes you notice the field rotation seems to be slow and then moving the other direction, which is surprisingly because of our eyes repetition of this sampling is quite limited and we interpret it as a different. So this happens all the time in our daily lives. Now let's move on to the performance characteristics of the measurement output. So when we quantify, how to quantify the quality of the measurement of the signal processing. The first is how accurate it is. So we can quantify our measurement between the true value and the mean of our measured value. So one easy way is true value, difference between mean value for positive measurement value, we divide by true and multiply 100. So this is quite well known. So that we call as a accuracy. Later on, when we discuss about the disease characteristics and measurement, we may use a little bit of a different definition. So the second is, in fact, the measurement is always involves a source of error and noise. So we have to measure sometimes multiple times, and we realize that how reliable or how reproducible our measurements becomes also important. So that's called repeatability. And that we call as precision, such that how precise our measurements are. So let me give you a kind of a rough figure here. So let's say center is a true value, and our measurement is first time, second, third, fourth, fifth, sixth, seventh, like this is distributed. You realize that these measurements, if we have a mean value, then maybe close to the center. Okay, while the other measurement system, let's say, gives this value. So they are like more concentrated in this area, which means it's more precise. However, that mean value is a little bit offset from the center. So in terms of accuracy, the left part has a better accuracy, while precision, probably this second measurement system has a higher precision. Okay, so precision, we can describe it as a standard deviation of the measured values. In fact, precision, to notify precision, we use a significant figures. So let's say we want to say, hey, this is 1 volt, then 1 volt versus if we have more precise value, 1.0 volt, which has 2 significant figure. So you probably have heard that, hey, the purity of, let's say, a copper as 99% versus 99.99999%, which describes the precision of this, the quality of the product. Okay, the last thing I want to describe is, remember that discrete value gives us a resolution. So resolution here, I will define as a smallest increment that can be measured in our measurement. So for digital output, this is 1 least significant bit. For example, let's say I have a camera which has 8 bit per pixel, and that 8 bit corresponds to 2.56 voltage. This range giving what will be our resolution of this camera in terms of, okay, not camera, but voltmeter with an 8-bit digital voltmeter, then what would be the resolution? That will be 1 least significant bit. So for example, 8-bit in digital binary system will have 2 to the 8th, which is 256 levels. You want to measure about 2.56 voltage with 256 levels, then you divide this and you will get the 1 least significant bit as a 10 millivolt. Let me reiterate this. So binary system in digital output, 8-bit is 2 to the 8th is 256 levels. So out of 2.56 voltage, you make it 256 level, then 1 level will correspond to the 1 least significant bit, or 10 millivolt. Okay, so now I want to discuss about performance characteristics of a measurement system. So let's consider performance of a system from the point of input to the output. So this is the input and this is output. Then the curve gives a change of input versus change of the output. So this is very familiar to you from the calculus concept, as this is a slope of this performance characteristics. And so this changes of output with respect to the change of input is a slope, and we call it as a sensitivity. Or if it's a system, then we call this a slope. So this is called the gain of a system. So in general, changes of an input, if output changes are bigger, then this is more desirable, right? So that higher sensitivity is typically better. And if the linear system, which means like twice of the input change will give twice of output, and that linear system, the sensitivity or slope will be constant. In general, our instrument system also has an offset. So for example, the same curve, we can offset this curve. And remember, the offset is just changing the y crossing or x crossing, okay? So which means in terms of the slope or sensitivity will not be affected by offset. So many instruments, in fact, has 2 knobs, a gain and offset. Offset to make it, let's say, like make a background as a 0. We use offset. And in fact, instruments are physical, and physical instruments are almost always saturated in extremely low and extremely high. So there's always a regimes, which is normal operating regime. So you have to check whenever you are using a bioinstrument. So this is a diagram showing that. So if there's a too small input, there's a zero sensitivity. And if you give the input higher and higher, it'll hit into this saturation. So that's a zero sensitivity. So you want to use it with this linear range, or it's desirable to operate them in the region of highest sensitivity. So this is kind of nonlinear. So we have to generalize for a nonlinear system. How do we define sensitivity at the point of input 0, and that instantaneous derivative or slope of output with respect to input, or local slope where input 0 is the operating point as a sensitivity. So you can see this input and output in general nonlinear system. You can define the sensitivity as the point slope, and you can make this as a lookup table. Okay, so next time we'll study about generalized Ohm's law, and thank you for your attention.